Hello and welcome to part 4 of the ARSET webinar, Satellite Remote Sensing for Agricultural Applications. Wherever you are joining us from, we hope you're keeping safe and healthy. My name is Sean McCartney and I'm an Earth scientist at NASA's Goddard Space Flight Center. In part 4 of the webinar series, we'll be focusing on evapotranspiration and evaporative stress index for agricultural applications. In part 1 of the webinar series, we provided an overview of satellite remote sensing for agriculture, highlighting specific satellites and sensors and how to access these data products. In part 2 of the webinar series, we focused on soil moisture using NASA satellite observations and modeled products that provide critical information for drought monitoring, agricultural monitoring, and crop forecasting. In part 3 of the webinar series, we covered some of the main products and variables for cropland and rangeland monitoring and showcased operational agricultural monitoring and early warning systems. For the final part of this webinar series, we are delighted to have as a guest presenter Dr. Christopher Hayne, a research scientist at NASA's Marshall Space Flight Center. Dr. Hayne's research interests include thermal infrared remote sensing with applications in surface energy balance modeling, soil moisture retrieval, hydrologic data assimilation, and drought monitoring. He's played a significant role in the development of the Atmosphere Land Exchange Inverse Model, or ALEXI. ALEXI is currently used to monitor continental evapotranspiration, soil moisture, and drought. Today, he'll be discussing the importance of evapotranspiration for agricultural applications, satellite methods for estimating evapotranspiration, case studies using the ALEXI model, an overview of the evaporative stress index, as well as highlight an exciting new evapotranspiration monitoring tool he and his colleagues created in Google Earth Engine. As with previous sessions, each webinar in the series will have a 1-hour presentation followed by a 30-minute question and answer session. As a reminder, both homework assignments are due by May 12th. If you are interested in a certificate of completion, you must attend all the webinars and complete all the homework assignments. You will receive a certificate approximately 2 months after the completion of the course from Marinas Martin. I will now turn the presentation over to Dr. Hayne to present on evapotranspiration for agricultural applications.
Okay. Thanks, Sean, for the introduction. As Sean said, I'm Dr. Christopher Hayne. I am a research scientist at the Marshall Space Flight Center in Huntsville, Alabama. And I've been working on essentially land surface remote sensing with a focus on evapotranspiration, drought, and working with a lot of agricultural applications for most of my career. And today I'll kind of give you a presentation on some of the applications that the community has developed for monitoring evapotranspiration, and then essentially some derivative products from these models to look at agricultural applications related to evapotranspiration and drought. So go ahead and get started. For the most part, what is evapotranspiration? It's an important part of the water cycle, as you see here in the schematic. We have everything from precipitation to how water flows back into the ground, is then available to vegetation. So when we talk about evapotranspiration, we're really worried about 3 main components of the water cycle, and that's evaporation from the soil surface. So a bare soil surface after precipitation, there's a certain amount of water remains in the soil, and near the land surface atmosphere interface, that water is available for evaporation. The other main one, and one that's probably the most important when we talk about agricultural applications, is transpiration from vegetation. So this is in the process of plants essentially taking in carbon dioxide and releasing water back into the atmosphere. Transpiration occurs because plants have large rooting structures. They have a lot of availability of water within both the surface layer and in their root zone. And transpiration really does make up a dominant part of essentially the exchange of water from the land surface back to the atmosphere. And then there's one other component. Essentially, this happens in very dense forest, in parts of the equatorial rainforests, Brazil, equatorial Africa, where you have very dense canopy structures. And actually, you get precipitation that is essentially intercepted by that canopy. There's water on the leaves, water within the canopy structure, and that can then also be evaporated back into the atmosphere. So these three components really come up with the summation of what we call evapotranspiration. Like I said, because we're kind of focusing on an agricultural application here, I really wanted to talk about, what kind of, this interface between the land surface and the atmosphere. So what controls transpiration from plants? And, the amount of water that plants can transpire, it can greatly change over geographical areas and over time, season. And there's a number of factors that can determine essentially how effective transpiration can occur from vegetation. The first one is temperature. Transpiration rates go up as temperature goes up, especially during the growing season when the air is warmer. So essentially during the cold season, when you have active vegetation, the plant does not, release as much water as when you have essentially in the warm season when you have more hot conditions, and this kind of goes with the atmospheric moisture part of the second control is warmer temperatures can hold more moisture, but also the amount of humidity or water vapor in the air also controls transpiration. As the air becomes more moist, the transpiration rates can fall. This is because there's not as much of a gradient between the leaf and the atmosphere. And so your ability for the plant to actually release water is lowered as the humidity rises. And this mainly means that it's easier to evaporate water into drier air than more saturated air. There is an additional consideration here that, when plants become stressed, when they have less soil moisture, soil available water in their rooting system, plants can also tend to regulate their own water use. So sometimes when plants become stressed and the humidity is very low, plants might pull back their transpiration rates to conserve water. So the moisture component is kind of a more complicated control, but generally, in a well-watered plant, it's easier for the plant to transpire into drier air than more humid air. The third one that we worry about is wind. Increased movement of air around the plant results in a higher transpiration rate. And this essentially helps because as turbulence can mix drier air near the plant surface, kind of tying back into that prior control, where it's easier to evaporate into drier air than the more saturated air. So when wind increases, it allows the plant to be more effective in transpiring. And then the one that I kind of was also talking about is soil moisture. When moisture becomes lacking, plants will begin to conserve water in a way of trying to, essentially not, go into a dormant state or to have, suffer from, essentially the ability for the plant to, essentially stay alive. And so it'll transpire less water. So these four controls, they're all kind of tied together in some sense, and no single one really dominates the structure. It's really this how they all interact together is really how we understand and understand how that plant interacts with the atmosphere and with that exchange of water. So now that we kind of understand what is ET, we'll call it ET going forward, evapotranspiration. Why do we need to measure it for agricultural applications? This is probably not a complete list, but this is, I think, maybe if you had to pick 5 ways that us scientists in the community work with stakeholders in the agricultural sector to use remote sensing data to measure ET. The first one, irrigation management. Essentially, in areas where crops are irrigated and not rain-fed, our ability to measure ET allows us to give better information to farmers on when and how much to irrigate. The second one, monitoring drought and crop stress. This kind of goes a bit with irrigation management. We want to make sure that we're able to measure ET so that we can find out when a plant may be undergoing stress. And in that sense, if it's an irrigated plant, you can work with the farmer to do a better management program. If it is rain fed, then you can start to hopefully have some mitigating factors for how to mitigate some of the impacts of drought and crop stress, or just to give an early warning of downstream effects when it comes to end of year yield, or impacts on a decreased amount of food that could be essentially harvested or grown from that crop. And that also goes into this third point, yield prediction. Through the growing season, a lot of scientists work with economists and others within the that sector to try to understand what the final yields of certain crops will be globally. And this is important for global markets, important for areas that are food insecure. So our ability to measure ET helps us when it comes to trying to predict what end of season yields will be. The fourth one, water use accounting. This is an interesting one because it's, once again, in areas where we may not have plentiful water, but yet we need a lot of water for irrigation practices. It's important for us to understand how much water certain crops use. And so this water use accounting is, and we'll have an example later in the presentation of how this works, but it's really important to understand how certain crops use water and how much they do, so that essentially strategies can be made to figure out what is the most effective use of the water in some of these areas like California, where we have essentially water security issues and not enough water to really irrigate as much as we would like to. And then crop water productivity, essentially somewhat the same kind of idea with water use accounting is how much how much of a crop can you grow per unit of water, and making more educated decisions on what crops to plant given areas where there is a limited amount of water. So I wanted to go through the next couple of slides talking about how we measure ET in a couple of different ways. First off, we actually have ground-based methods for measuring evapotranspiration. And the two main ones are essentially eddy covariance. These are instruments that are essentially put on towers over a field, over an area where you would like to understand kind of the dynamics of evapotranspiration. And essentially it's looking at really, really fast measurements of fluctuations of vertical wind speed and essentially water vapor. And by looking at those very, very fast changes and fluctuations, we're able to estimate how much water is being evaporated or transpired from the surface. As you might imagine, these systems are complicated. It takes a very specialized person to understand how to actually place these to get the most accurate measurements. And it's not like going out and measuring a temperature with a thermometer. There's still uncertainty in air with even these observational systems. So that's very complicated for measuring ET, is that even our quote unquote ground-based observation systems have uncertainty. We don't necessarily measure it as perfectly as we can measure other things. But these are kind of our ability to have some ground truth to these measurements. And the second measurement is called a lysimeter. It's another relatively complicated observation system where you're actually building an apparatus within the soil surface that's able to weigh the soil column continuously and essentially back out how much water has been evaporated by changes in the weight of that soil column. I think the other real take-home message is both of these methods are pretty cost prohibitive. They're very expensive to build, they're very expensive to maintain, and frankly, that's why we only have several hundred of them to measure ET globally. So, having direct measurements of ET from these observational systems is not something that we could do everywhere. It really serves as the ground truth and the validation for some of the methods we'll talk about in the next few slides of how we measure ET from both a modeling standpoint and a remote sensing standpoint. So models. Um, there's a couple of, ways that we can essentially, much like we use models to predict the weather, we can use models to predict energy, water, and momentum fluxes between the land surface and the atmosphere. Essentially, we derive and build computational models to use these physics to understand or to model what we have as an understanding of that interface between the land surface and the atmosphere. So with land data assimilation systems and land surface models that are able to predict these energy and water fluxes, we constrain them with essentially observed atmospheric conditions. We know the temperature, we can measure the wind, we can measure the humidity. And then essentially we have models within, or physics within those models, to estimate rates of evapotranspiration, changes in soil moisture. So everything that we understand about the system, we put into these models. Unfortunately, we don't always have the most accurate observations to force these models, and a lot of the physics are very complicated. And so we have to really parameterize, which is essentially a way of making some broader assumptions about how some of these physics work when we don't have the observations to truly model them to the most, accurate sense. And so, from an advantage standpoint, these models are nice because they can be run anywhere where you have the forcing data. Um, you know, Even if that forcing data is coarse or maybe not as accurate, take for example, Africa, we don't have a lot of ground-based meteorological information compared as to, an observational network over the United States. So that introduces some uncertainty. Another advantage is that, it provides complete temporal resolution and, information of ET over the day. You can run the model and output what the model is estimating ET at any time of the day. So it gives you a full, complete temporal picture, and you're able to run these at varying spatial resolutions. Some models run all the way down to 500 meters or 1 kilometer. Some global ones are more on the 5 to 25 kilometer. So you have a lot of flexibility in what you want to model. Disadvantages. I mean, with anything with ET, every method will have its advantages and disadvantages, and it's not so much that we have a clear-cut way to model, or either from a model or a remote sensing standpoint, to estimate ET. We really have to kind of work within the constraints of each method to give us a more complete picture. So the disadvantages of models, like I said, we have errors in atmospheric forcing. The main driver to land surface models is precipitation. If your precipitation is not right, you're already starting off with some level of uncertainty in what the soil moisture will be, and then the downstream effects on ET accuracy. If your precipitation is poor, your soil moisture prediction will be poor. That will affect your estimation of evapotranspiration. So really, the errors in the atmospheric forcing can cause a lot of issues with producing essentially less certain estimates of ET. And also, we can experience model drift, and this happens where essentially these errors accumulate. Errors in the forcing or the model physics can accumulate, and we can get to a point where a model becomes biased, it becomes too wet or too dry, and so all these errors and all this uncertainty essentially kind of downstream feeds the additional uncertainties, and especially in this case, the measurement we're trying to model is ET. So you have to kind of take all of this into effect and try to understand what your best method for estimation is. So that gets us into really what the core of some of what our work is focused on, which is using satellites to estimate evapotranspiration. There's a number of different methods to do this. I start off here with one of the more simple methods, but it's a very strong method when you're looking at trying to estimate ET for agricultural applications, especially when you know a lot about the crop that you're trying to measure ET. So in a crop coefficient, or ETO, which is a potential or a reference ET, I'll get to what reference ET means in a minute. So essentially, we're trying to calculate evapotranspiration by computing a measure of what the reference ET is. Reference ET is essentially the amount of ET that would occur under well-watered conditions. And we can estimate that from an agricultural weather station because it's a function of things like solar radiation, temperature, moisture, all those atmospheric controls that we talked about earlier in the presentation. And then applying a crop coefficient. So essentially, a crop coefficient is very specific to a given crop. And it tells you how much, given the reference ET, you would expect that plant to transpire. That being said, those crop coefficients are, it's really good when a farmer is able to understand what crop is in his field or her field and to apply a crop coefficient that is relevant. And so this requires a lot of human interaction to try to, do this in a way that, is able to provide an accurate measure. And so one of the established methods is a NASA program that's run out of NASA Ames, the NASA Satellite Irrigation Management Support System. And this uses a crop coefficient method over most of the Western United States, especially in California, where we have good remote sensing information and good crop data to come up with an automated way to estimate crop coefficient based on NDVI and estimates of crop height and estimates of what crops are grown in what field. That being said, the main limitation of this method and why it's a good agricultural method for irrigated agriculture, but maybe not so good in rain-fed agriculture, is that there is less sensitivity to changes in ET related to deficit irrigation or changes in stress. It's really good at estimating evapotranspiration when we have a good understanding that the plant is well watered. And as we go to the next slide, this is really where a lot of the next method, being focused on energy balance methods, or maybe more broadly applied to different types of agricultural applications and actually monitoring ET over, lots of different ecosystems, forests, grassland, wetlands. And so the real theory behind a surface energy balance method is we know how much energy is coming at the surface from shortwave and longwave radiation. We can measure that with meteorological data and satellite data. And the amount of energy available at the surface is balanced by fluxes from surface heating and the exchange of water vapor. So the exchange of water vapor being ET. And so we know, given all the energy that comes to the surface, how it's partitioned between heating the surface and then energy that's used to evaporate water from the surface. Really, energy balance models can be divided into two categories. One, a single source energy balance model. This is where the model takes the vegetation and soil and analyzes it in a combined energy budget. These were essentially the first energy balance models kind of conceived, a number of decades ago. One of the disadvantages is that, the exchange of heat and moisture from the vegetation and soil are handled very differently. So when you combine them into one energy budget, it requires a lot of assumptions and kind of corrections that make single source energy balance models sometimes hard to apply in an automated sense without this calibration. To kind of address some of those issues, a number of researchers have, essentially developed two source energy balance models, which handle the vegetation and soil energy budgets separately. And this gets away from having to do that calibration or that correction of considering the vegetation and the soil as one component by allowing the vegetation and soil, which can then be categorized given its actual characteristics in a two source energy balance model, has been shown to lead to more accurate partitioning between the energy fluxes between vegetation and then bare soil. So I won't go into many of these, but I left them here for just kind of an example of some of the methods that have been developed over the last number of decades, and then the relevant citation that anybody can go and kind of read up more on these. But these are kind of not, like I said, not a full list of energy balance methods, but really represent some of the foundational development of these types of methods. And most of these methods have been continually developed, and you'll see as we go into the presentation where some of them will pop up. My background has really been with the atmosphere land exchange inverse, Alexi and Disalexi model, which is a two source energy balance model. The Alexi component essentially is the global or regional version that runs on moderate resolution. And then dyslexia is the essentially the high resolution field scale estimation tool that uses high resolution remote sensing information from sensors such as Landsat and Sentinel-2. And we'll talk some more about that as we keep going. So, like I said, most of the rest of the presentation will focus on Alexi and some of the applications that we have developed for agricultural and other applications, both in measuring evapotranspiration and looking at drought and vegetation stress. But like I said, I think the main take-home message is that all of these, even the energy balance models, all have their advantages and disadvantages, and have been shown to be, some models perform well in some, some regimes, and some perform better in other regimes. And the real take-home message, the ET community, especially from a remote sensing standpoint, is rather collaborative. And you'll see that as we get to the end of this presentation and some of the future work that we're doing, is that really the community is moving towards looking at estimation of evapotranspiration from an ensemble standpoint of understanding when we get more certain estimations of ET if we take an ensemble of methods rather than relying on just one method that may do well in one regime but not do well in another regime. And what we're finding is when we are able to understand the advantages and disadvantages of each of these methods, providing an ensemble with both provides us a better, more accurate estimation, and then also a level of uncertainty, which is something we'll always deal with measuring evapotranspiration, is trying to minimize the amount of uncertainty, but understanding that even our observational systems are not a direct measurement, and neither are our remote sensing or modeling methods. So this is a little bit of a maybe difficult a difficult slide to look at, but we'll try to walk you through some of the physics of some of this, at least Alexi in an energy balance sense. So what you see on the left is essentially the representation of a two-source model. You have essentially resistances that explain the exchange of heat and water, or heat and water from the bare soil surface, and then the exchange of water and heat from the vegetation surface. And then those are essentially coupled with essentially the atmosphere above them, and then the exchange between those two components in the atmosphere. That blending height you see there, that's kind of, think of it as the an interface between the atmosphere and the land surface. So really, to estimate these fluxes correctly, you need to know the temperature at that blending height. Unfortunately, we don't have a way to directly measure that height. We have models, but if the model is not consistent with what you're seeing with the remote sensing data, those will not be, they'll be out of, they won't be consistent. So it can lead to large errors in what we see. So the main real additional development for Alexi from its original two-source model implementation was to couple the two-source energy balance model with a boundary layer model above it, so that we can actually model that temperature at the blending height based on what we were seeing from the changes in land surface temperature. So land surface temperature, we measure that from satellite, and Alexi is really driven, and most of these energy balance models are driven by that land surface temperature. Alexi uses a change in land surface temperature in the mid-morning. That's been shown to be coupled with that partitioning between heating and evaporation. Because evaporation is a cooling process, a satellite pixel which is evaporating at a high rate will heat up slower than one that is drier and not evaporating at a higher rate. So that's the main core of the physics of the model, is using this change in land surface temperature to understand how much of that energy is being converted into evaporating water from the land surface back into the atmosphere. And so this coupling of the boundary layer model allows us to keep these two systems in balance, and gets us away from having to measure that temperature at the blending height. And that's really, one of the main additions of what essentially has become this model that we've been developed in the 90s and now still used today. So one more way of kind of looking at this is, what you see here is on the left is a water balance approach. So think of this as how when we were talking about land surface models and land data assimilation systems, these are all the physics we had to try to parameterize, and mainly driving this was the precipitation, um, and understanding how all of these systems interact to be able to estimate transpiration and evaporation. For an energy balanced approach, essentially what we're doing is, like I said, we're giving the known radiative inputs, and we can calculate how much water has to be lost or evaporated back into the atmosphere to keep the soil and vegetation at the observed temperature rates. So there's two different methods, but one of the advantages that we're measuring evapotranspiration with these two methods, yet they're being driven by essentially observations that are not do not have correlated errors. So when we have both of these methods giving us consistent estimates of some of these energy fluxes, it gives us a little bit more certainty that we're getting. So that's why when we talk about having an ensemble approach to estimating evapotranspiration, that's really what we're trying to do, is have different methods of trying to get at the same observation, and when those agree, it gives us more certainty that we're measuring them accurately. Real quick slide, this kind of shows the real power of this multi-sensor, multi-scale ET mapping system that we have with Alexi and Dysalexi. Like I said, mainly driven by land surface temperature. We measure land surface temperature at varying spatial and temporal resolutions. We have geostationary sensors that measure land surface temperature over most of the globe in the more moderate resolution, 2 to 4 kilometers. We have polar orbiting sensors such as MODIS and VIIRS that can measure twice daily land surface temperature at the 375 meter to 2 kilometer range. And then we have much higher resolution information from sensors like Landsat that give us, essentially once every 8 or 16 day measurements of land surface temperature at the field scale. So being able to understand a modeling system that's able to consistently balance energy inputs across all these scales really shows the power of our Alexi modeling system. One of the issues with Landsat is that we only get it, once every 8 or 16 days, and we need those retrievals without clouds. So, sometimes we have areas where we can go a number of weeks without a clear Landsat overpass. And sometimes the change in ET is occurring on timescales that happens in between Landsat overpasses, where you may get a rainfall event and you may not see the impact on the evapotranspiration until the next Landsat overpass. So what our team has really focused on is finding ways to integrate moderate resolution into our modeling system. And so what you see here on day 328 and day 336, we had 2 Landsat overpasses. And then deriving information between relationships between MODIS and Landsat, we were able to fill in the 30 meter ET based on the MODIS overpass on those other days. So giving us a full daily estimation of field scale evapotranspiration. And as we look here, this is kind of an example of what happens. So this is a time series of evapotranspiration over a cornfield in Iowa. And what you see here on this top chart is that the red squares were Landsat overpass days. And without this kind of data fusion of fusing some of the moderate resolution information, as you saw, there was a number of rain events in between those 2 Landsat overpass days. And that red dotted line is essentially what the ET would have been if we had just not used the MODIS information in between the Landsat overpass days. And then that dark red line was diffusion. And that the blue dots are essentially the observation. So you see the data fusion really was able to capture these rain events in between Landsat overpass days. And the real take home message on the bottom plot is with the solid red and the solid blue line, our data fusion method matched observations much closer than if we had just only used Landsat. So it really shows the power of this integration of moderate resolution LST, or land surface temperature, into the modeling system to get at some of these changes in evapotranspiration in between Landsat overpass days. Another real interesting application is, starting to then integrate even higher resolution um, land surface temperatures from, we can do this from unmanned aerial vehicles, aircraft, where we can really start to get at intra-field ET variability. So this is an example of ET over a grape field in California. What you see here on the left is essentially the yield, and as you see over the over the field, there was a large variability in actual yield. Some areas had much higher yield than other areas. And we were able to start to see that with both the Landsat ET at 30 meters and this aircraft, that water use can vary can significantly vary over a field. So this really is the power of getting this type of information into the hands of agricultural stakeholders, because they can make decisions on why certain parts of the field may be stressed. A lot of times this has to do with the dynamics of soil, drainage. So it really allows them to understand water use within a field, not just looking at something that might give them one picture of like their field from a lower resolution. Really allows them to understand what essentially what they ended up getting and yielding at the end of their season, and essentially the water use dynamics during the season within that field. I'm going to walk kind of through a case study. And this is essentially, we've been working a number of years with, E&J Gallo, which is a large wine producer in the Central Valley in California. And they have really shown a lot of interest in trying to integrate remote sensing information into essentially their management practices within their vineyards. So we've been working on this GrapeX project for a number of years, measuring essentially field scale evapotranspiration in a number of their research fields. And two of the sites here are near Lodi, California. We've been measuring ET for them over this region for, back from 2013 to present. And we're actually trying to do this in real time so they can actually make decisions on how to irrigate and manage their vineyards. This is another example of just kind of like the year-to-year variability in these two fields, and essentially a validation. We have eddy covariance flux towers in each of these fields to kind of validate some of the methods that we're developing. And as you see here on the top, you see kind of the change in water use over the 3 years here, 2014 to 2016, and then a time series of both the modeled and the measured. And for the most part, we underestimate a little bit sometimes in very high evaporative demand. Sometimes, these scenarios where you get a lot of dry, hot air. This particular field being in the hot portion of the Central Valley in California, it can be very hot. And measuring ET under those conditions sometimes is the most complicated and difficult. But for the most part, we've shown good validation of the method for over vineyards. Another example here, this is another thing that's focused on the San Joaquin Valley in California. As I mentioned earlier, water accounting is another really important tool. We're really trying to understand in this river basin where the water is being used. What you see here on the right for 2015 and 2016 is the USDA crop data layer that tells us essentially in every field what kind of crop was being grown. And you see it in the legend that we have everything from corn to alfalfa to tomatoes to vineyards to almonds to fields that have been fallowed or not being used that season. And then an estimate of our Alexi evapotranspiration for a 10-day period during the peak of the growing season. This show you that certain crops use a lot more water than other crops, and that's really where water accounting comes into play, of trying to understand the dynamics of how much water is being used and for what. So exactly, this kind of is the take-home message. So because we were able to measure evapotranspiration at high resolutions over this area, and then we had high resolution information about what was being grown in each field, we were able to actually break out water use per unit area by certain crops. So some of the bigger water users, almonds, rice, walnuts, olives, and then you have some of the lower water use crops like tomatoes, vineyards, pistachios. So it really gets to the point where understanding where every unit of water goes and to how effective a certain crop uses a unit of water. And then we can do something like this where we actually can use over the season, understand when crops use the most water. I think this is an interesting thing. You get this kind of peak in the rice crop where it's using a lot more water than other crops. Um, but ultimately, you get a sense of how much water is being used to produce a certain amount of food. And so this is very important for areas that are trying to do a better job of managing, essentially a finite amount of water, like in an area where California, where agriculture is a very important economic sector, but there's only so much water and limits on pumping water from the ground. And so it's very important to have methods to understand how water is being used. So one other thing, this kind of is something that's been an important integration of a new observation into our modeling system. So, our method really does rely on, the thermal infrared wavelengths to measure land surface temperature. So these only allow us to measure land surface temperature and then subsequently evapotranspiration when there are no clouds. And that can be problematic in a lot of areas. We can go. There are areas in equatorial Africa, the Ethiopian highlands, where even during the growing season, they can have drought and crop stress, but we don't, because it's such a cloudy area, we don't actually get enough real certain clear sky retrievals to get a good understanding of what's happening on the ground. So this led us to really trying to figure out how to exploit microwave wavelengths, which are not as sensitive to clouds. They can see through clouds to measure land surface temperature, as long as there's not heavy precipitation within the cloud. So it gives us a lot more information, albeit at a coarser spatial resolution. But still, coarser information is still better than no information in a lot of these areas where the integration of microwave land surface temperature is really helping us get more certain estimates of land surface temperature and subsequently evapotranspiration. So here's just an example over equatorial Africa and the Ethiopian highlands. As you see here on the left, this is an estimate of evapotranspiration just using thermal infrared. So as you see kind of in the equatorial rainforest, we get a lot of this speckle and noise, and that's just because of the uncertainty of being able to clear out the clouds. That contamination gets into our system and it causes us to have errors and uncertainty. If you look at the microwave version, we don't have that, and so we get a much clearer picture of what's actually happening. And in this sense, the cloud issues were really causing us to underestimate evapotranspiration in a lot of these areas, where the microwave gave us much more certain observations with a lot less variability and noise. And so this actually will feed downstream into our higher resolution information, because what we're essentially retrieving at these scales serves as that boundary condition for those Landsat scales. So we have to measure ET at this scale correctly first if we expect to measure it accurately at the Landsat scale. So we're going to switch topics slightly. We're still going to be talking about evapotranspiration, but kind of looking at it from a case study of looking at how we use some of this information to monitor and provide early warning for agricultural drought. I show this a lot when I talk about drought. This is kind of how the atmosphere and some of the remote sensing timescales for drought early warning kind of go hand in hand. As you see in the top, usually the precursors of drought are either one or both of these two real atmospheric drivers. High atmospheric demand. So atmospheric demand is the thirst, all those controls we talked about before: temperature, wind, moisture. When all of them kind of all point to enhanced evapotranspiration, it can very rapidly dry out the land surface. Those tend to be correlated with periods of below normal precipitation. So you have a high thirst of the atmosphere pulling water out of the land surface, and then below average precipitation or recharge of that soil moisture. Um, so you can start a growing season with sufficient soil moisture. As you know, these atmospheric controls start to lead to degradation of the surface soil moisture. You can measure that with microwave soil moisture. Um, as the root zone dries out, you start to see onset of vegetation stress. Our thermal-based method with Alexi and a derivative product called the evaporative stress index, which I'll talk about in the next slide, really is looking at the plant dynamics of the onset of vegetation stress. And then, you look at something where the vegetation is now to the point where it's becoming damaged, it's turning brown, it might not be as green as it's supposed to be. You can start to use NDVI to see that. So really, you've got to use these different observations because they represent different time scales of the process um, in an agricultural drought. So I'll talk about two real new, relatively new products that are focused on using, essentially both evaporative demand and actual evapotranspiration for looking at drought. The first one is called the Evaporative Drought Demand Index, or EDDI. It really uses the strong physical relationship between demand and actual water loss. And like I said, demand can really be explained as the thirst of the atmosphere, or how much water would evaporate for the land surface under well-watered conditions. So EDDI really provides a signal of potential for future drought by looking at essentially how thirsty the atmosphere is to essentially estimate the potential impact on the land surface. The one caveat with EDDI is that it doesn't actually physically tie to actual land surface conditions. It can only show you the potential for the development of drought. It can't actually show you actual drought in isolation because it doesn't have any information. It's just an atmospheric indicator. It doesn't actually know if the plant is well watered, what's the soil moisture conditions, or what's the actual evapotranspiration. So it's really just, it's a tool that has to be used with other tools to validate if there's actually an actual tie back to the land surface that we're actually seeing impact in evapotranspiration rates or soil moisture, to really validate if EDDI is showing that potential for drought, if it's actually turning into an actual drought. And this is just an example. The website here, they run EDDI, kind of in a near operational, near real-time manner, to kind of track changes in this evaporative demand index for drought. So the one that our team has developed is called the evaporative stress index, and what we're really looking at is anomalies in the ratio of actual to potential, or that thirst. Potential is that thirst of the atmosphere. But because Alexi gives us actual ET, we're actually able to tie both actual ET to the potential, which gives us a physical tie to what's actually happening on the ground and within the plant. One of the advantages of ESI is that it doesn't require precipitation data. We're deducing the soil moisture straight directly from land surface temperature. So we don't need to know precipitation. We don't need to know soil moisture. We're deducing the current soil moisture state of the vegetation directly by this land surface temperature driven model. It provides early warning because we can start to see signals in the land surface temperature before you start to see deterioration of vegetation health. That's because plants are relatively smart. Plants will start to regulate their water use by closing their stomata and limiting transpiration when they become stressed. This leads to essentially, remember, because evaporation is a cooling process, if it starts to slow its evaporation in a way of trying to conserve water, the leaf temperatures are going to heat up faster. We see that with the land surface temperature that we can retrieve from satellite. So essentially, we're seeing that onset of stress before the plant's actually looking like it's damaged or decreasing its greenness. Another big advantage is that we include non-precipitation moisture signals. I don't need to know if a plant or a field is being irrigated. We don't need to know if vegetation is rooted to the groundwater. Because as long as we can measure the land surface temperature, we are seeing what the plant sees. And that allows us to know if there's being some impact from a drought to changes in water use. This is just an example. We run this model both regionally and globally. This is a version of our global model. It kind of looks what it looks like. Um, uh, Towards the end of the presentation, we'll have some links to where you can get this data and look at it. We run this model in near real time too, and all the retrospective and real-time data is hosted on Amazon Web Services and made available to the community for use. So we'll definitely provide that to the participants at the end of the presentation. So some of you have kind of maybe started to hear this idea of like flash droughts, these rapidly occurring. We've had a number of them over the United States in the last couple of years and decade, elsewhere in the United States, essentially where we can go to from relatively normal conditions to, very dry and anomalous drought conditions in a matter of weeks to a month. Most people think of drought as a slow evolving phenomenon. What we've learned though is that in especially agricultural interests, we can have these flash droughts, which are really just been driven by precipitation deficits, hot temperatures, strong winds, um, less clouds, so you have more solar radiation, more energy at the surface to evaporate. And this is an example in 2017 of a very damaging flash drought in the Dakotas and eastern Montana, where, as you see in early May, we had mostly normal to a wetter than normal conditions. 1 month later, most of the Dakotas were in pretty significant drought, and then by the beginning of July, most of the area and a lot of the agricultural interests, both from a crop and a rangeland standpoint, were in significant D2 to D4 drought. And the economic impacts of these flash droughts are significant, and our ability to try to mitigate and understand and provide early warning of them has become a real thrust of new research in the drought community. And these ET methods, such as ESI and some of the other methods, have really shown the ability to provide us some early warning so that some mitigation strategies can be applied. Another application, we talked about crop yield anomalies and predicting those. What we're also understanding is one way of trying to better predict crop yield anomalies is understanding water conditions through the growing season. Some crops are, yield is driven by, or changes in yield can be driven by when stress is occurring within the crop stage. For example, corn, there's a certain part of the corn growth stage where if it experienced stress, it's going to lead to significant degradations and final, end of season yield. This is really highlighted. I'll try to walk through this slowly to try to understand. It's an interesting case study, and it's one that's close to home here because it occurred in northern Alabama. But during the 2012 flash drought, as you saw here, if you want to focus on the corn, we had negative corn yield anomalies here in northern Alabama and Tennessee, where essentially the stress occurred when it was in that pivotal growth stage. We got out of our flash drought relatively quickly at the beginning of August and September, and we had much less stress for our soybeans. So we actually had above average soybean yield and below average corn yield just because of when the flash drought occurred here. So it shows that it's not so much, in a season, did a flash drought occur? It's when did the crop go through the stress, and at what stage did it happen? And so this has just been, these case studies that we continually develop over as we go through more growing seasons to understand how to use this information to provide better estimates of crop yield anomalies. So I'll kind of close with a couple of slides for maybe some future stuff. Our research team, along with a lot of the researchers that you saw from some of the other energy balance models, have all worked together to kind of build this Google Earth Engine ET monitoring system to look at essentially field scale evapotranspiration for agricultural applications in the Western US. Water issues in the Western US are really big and really important, and having a means to estimate evapotranspiration in real time is very important. So this project called OpenET, it's, we're still under development. I have the link there if you want to start taking a look at it, but over the next couple of years, you'll start to hear more about this. And I'll kind of just walk you through some of the examples of, being able to have essentially a cloud-based platform where a stakeholder can go in and essentially, interrogate water use using a number of different methods at these field scales, and produce reports and have an understanding of the water use of different crops in the Western US. So now I'll just finish up the presentation with a couple of slides about a new mission that was launched in the last couple of years. A lot of you probably have heard of it, EcoStress, which is a thermal imager that is on the International Space Station, on one of the science ports on the space station. This is essentially a Landsat-like sensor from a thermal standpoint. So it just has 5 thermal bands, essentially at a resolution of between 40 and 60, 70 meters. One of the issues is that we don't have the visible and near infrared information that we need for some of the vegetation information. So we essentially fuse that with the closest Landsat overpass, which creates some issues with making sure that the 2 images are consistent. But given that, you know, we have limited thermal information as it is, this is still an important addition to looking at how to estimate evapotranspiration from thermal infrared observations. What's nice about this sensor, because the orbit of the International Space Station is obviously different than what a polar orbiting sensor might be. We have a much higher revisit time, on the order of 4 days, where 4 days, you know, essentially, you know, near the equator and in the tropics. And then sometimes as we get, you know, because of the orbit of the International Space Station, we only get coverage from about 50 south to 50 north in latitude. And because of that, we get more frequent observations over a belt essentially from 40 to 50 degrees of latitude. So it's an interesting orbit. It gives us obviously more information than we get from some of the thermal information that we get from Landsat. And the other really interesting part, which is one of the science questions that EcoStress really tried to focus on, is, you know, with Landsat, we get a thermal overpass at the same time, roughly every time it overpasses the point on the Earth, and that's in the late morning. Because of the orbit of the International Space Station, we actually have a variable overpass anywhere from 7 to 5 p.m. local time, 7 a.m. to 5 p.m. local time. So it allows us to look at thermal signatures during different parts of the day. This is important because a lot of, you know, from an agricultural standpoint, we might look at stress occurring in the late afternoon that we wouldn't necessarily see from a late morning observation in Landsat. And so that are some of the science questions we're trying to ask. If you go to the next slide, this is kind of what you can get at. This is essentially some center pivot irrigation agriculture in the Nile Basin in Africa and Egypt. And as you can see, these are 2 different overpasses, one occurring in the morning and then one occurring in the afternoon. And so we're able to actually look at water use dynamics throughout the day, where from a Landsat standpoint, we'd only ever keep getting the same observation time for each of the overpasses. So this is really kind of shows some of the capability, and you can follow the link here and learn more about the EcoStress mission. And it's been flying, I said, for a number of years, and the data is available, and, you know, hopefully we can continue to justify the use of EcoStress on one of the science ports on the International Space Station. We'll continue to have these observations at least for a couple more years. So from that point, I'll stop and we can move to the question and answer session.
Thank you, Chris, for such an informative presentation. This provided a great conclusion to the webinar series, and on behalf of everyone at ARSET and from those online, thank you. As a reminder to our participants, if you have a question for Dr. Hain, please include them in the chat box. We'll get to as many as we can in the time remaining. As with previous question and answer documents, they will be posted to the training page by next week for you to access. Below is the contact information if you wish to follow up with any of the trainers. We will now proceed to the question and answer session. Well, thanks for everybody for sending in your questions. Looks like we've got quite a few of them for Dr. Hain. So I guess I'll start off with the first one. Question 1 is, which types of satellite images are suitable for analysis of evapotranspiration for large SETI areas?
Can you hear me?
Yes.
Okay, good. So yeah, for this question, you know, it really depends on what application you're going after. You know, most of the energy balance methods that we presented here rely on thermal infrared imagery. You know, for the model that, you know, I work with, Alexi, we run with essentially moderate resolution land surface temperature, from a geostationary satellite. So we're really looking at that mid-morning rise in land surface temperature. Those are on the scales of 2 to 4 kilometers. If you really want to understand evapotranspiration for an agricultural application at the field scale, you really need to get down to that Landsat, 30-meter eco-stress, 30-meter scale. So really it's dependent on your application, and that's that's kind of just it's hard to answer that as for example from a just a general question, but I think as we showed with kind of the multi-scale version of our model, there's ways of integrating these thermal information that you get at different scales. So that's hopefully that kind of if not, if there's a follow-up to that, I'd be happy to address a specific application.
Great. Question 2, does the evapotranspiration decrease before the growing seasons in crops?
Well, generally, yes. So think about, think about what goes into, say, let's start with potential evapotranspiration. What would happen in a situation where the land surface was well watered? What then drives the actual amount of evapotranspiration is things like sunlight, incoming long wave, that balance between the incoming and outgoing short wave and long wave radiation. So essentially we call that net radiation. So obviously during the warm season, net radiation is higher. During the cold season or the non-growing season, it's lower. And a lot of that comes with the changes in the amount of solar energy that we get from the sun. So generally, yes, less evapotranspiration in the cold season, non-growing season, more evapotranspiration in the growing seasons. And that's kind of why we have growing seasons and non-growing seasons.
Great. Question 3. How can yield be predicted from ET for a particular area, say Africa?
Yeah, I mean, so, the hardest part with trying to predict yield is you really need good observed yield from previous years to try to, build relationships between, if say we have 20 years of evapotranspiration data and then 20 years of good quality yield data at the field scale, you can start to build, machine and deep learning methods to try to predict yield. And, there's a number of people in the community who are doing that. It's definitely it's definitely done more on a local or regional scale. There are people who are doing, continental type scale yield predictions. But yeah, I mean, it really is predicated on having good training data to try to build a method or tool to predict yield. But obviously ET is a very important quantity for how, trying to build that relationship between what has happened in the past related, with respect to ET and then, what was subsequently happened in those years from a crop yield standpoint. And obviously, there are a lot of other indicators and data sets that would be needed to build such a tool. But yeah, I mean, they're definitely, I think the community has moved and has made a lot of progress in the last number of years at developing methods to look at this. So I think it's a very important, science question for the community to focus on.
Great. Question 4. I'm not clear about the difference between potential evapotranspiration and actual evapotranspiration. Would you clarify the difference, please?
Yeah, so think of potential as, what would happen if all of the conditions or all those drivers that control evapotranspiration were optimal. Well watered, sufficient soil moisture, lots of, solar insolation. So essentially what would happen if there was no constraint on evapotranspiration? So that kind of sets that threshold for what would happen under those conditions. Actual ET is what actually is occurring. It's more of a physically based estimate of how much water is actually being transferred from the land surface to the atmosphere. So that's really the difference. Potential is kind of what would be happening under optimal conditions, and actual is actually what is happening.
Great. And question number 5, can we use interpolation methods to measure evapotranspiration?
I'm not 100% sure what whoever submitted the question meant by interpolation methods. You know, we do rely on using interpolation to try to estimate, seasonal or annual ET, especially at the field scale where we only get Landsat overpasses, under a best case scenario, every 8 days. So we do need to find ways to essentially take those sparse observations and then estimate ET in between Landsat overpass days. And you see with the method that we presented today that, one method is fusing, slightly less, more moderate resolution from VIIRS and MODIS to fill in for some of those gaps where, it's complicated if you get a Landsat overpass at the beginning of the month and then one at the end of the month. It may not represent rainfall events in between those two overpass days. So the introduction of more moderate resolution days that, that's available on a daily time scale could hopefully fill in some of that information, and albeit at a coarser resolution, but we've developed data mining machine learning tools to try to make those essentially the information we get at those scales and be able to interpolate it down to estimate the field scale. So while I say you can't use not really use interpolation methods to measure ET, there's a lot of interpolation and data mining to try to fill in some of the observational gaps we have. So it's definitely an important part of the process.
Great. And question 6 looks like it's a 2-part question. So the first part is there any recent model to drive ET or energy balance with the absence of in situ data? And then the second part of that is, what is the best way to estimate ET using only remote sensing?
Yeah, so in some of these energy balance models, we don't necessarily need in situ data. So a lot of those methods that we like I said, when we presented from the energy balance standpoint, that's part of what remote sensing addresses with some of the issues where trying to get at evapotranspiration without in situ data. Obviously, it's not fair to say we don't need any in situ data. I mean, you need to know what is the land surface you're looking at. It's helpful if you know what kind of crop it is for some methods. And so, and sometimes, especially in areas where you have irrigated agriculture and more arid conditions, some of the say model data that we use to kind of initialize what the atmosphere is not representative of what's actually going on the ground. So sometimes in situ data is helpful to correct some of those errors. So it's probably not fair to say that we don't need in situ data. I think when we have in situ data, it makes the methods more robust. But generally, a lot of these remote sensing methods do not rely on in situ data. For what is the best way to only use remote sensing, I think what we're finding is, we have a number of methods from an energy balance standpoint and a crop coefficient standpoint and other methods that all have their strengths and weaknesses, and no one single model has shown to be what would be considered the best way to do it over different regional areas or different ecosystems. So that's really why, when you saw some of the slides from the OpenET project, it's really, all of these different modeling groups coming together and, realizing that it's better to work together than to compete, because nobody has the best method. And understanding when certain methods do better over certain areas and then using an ensemble of methods tends to give us the best validation when we actually compare against actual ground-based measurements of ET where we actually have eddy covariance flux towers. So it's really that multi-model ensemble which is the best way to estimate ET from remote sensing. At least
and Chris, it looks like question 7 is actually very similar to question 6 as well. But given that the ground observation data are scarce in Africa, which models and remote sensing approaches would provide good estimates of ET?
Yeah, I'd probably answer it the same way. I think, these energy balance models don't rely on in situ data. Some of the crop coefficient methods that we talked about briefly really need good crop data layers to, do an accurate estimation of the crop coefficient, which I guess I'll just address question 8 too. So a crop coefficient is essentially, once you estimate potential evapotranspiration or some reference ET, potential evapotranspiration and reference evapotranspiration are kind of similar. So a crop coefficient is, say for corn, has a certain crop coefficient that to estimate ET, you would take the reference ET and multiply it by that crop coefficient. So it's essentially how effective a crop is at, you know, producing transpiration. And so because some crops use more water, some crops use less water, that's why we have crop coefficients to represent those changes in water use dynamics across crops. So I think that's probably the best way of looking at it.
Great. Question 9, could you explain or any recommendation to estimate surface energy balance using satellite data, especially for places that lack insufficient in situ data?
Yeah, so I mean, I think, this is also similar to question 6 and 7. I think a lot of these energy balance models don't require in situ data. So they're able to be applied, in areas where there is insufficient ground-based data. You know, because remote sensing provides us a large, it provides us information that we need for these methods everywhere. And there's enough also shortwave and near infrared observations that we can categorize or characterize the vegetation correctly in these areas where we don't actually have ground-based observations. So yeah, I would refer back to question 6 or 7. I mean, I think it's really an energy balance question of, you don't necessarily need in situ data. It can be helpful in cases, but it's definitely not something that is necessary.
Great. Question 10, the remote sensing approach of estimating ET is good and well for estimating and or determining potential ET than actual ET. Is that not? Essentially, the actual ET contains the soil moisture stress component in it. Could there be any way to include the soil moisture stress component, KS, and compute the actual ET better?
Well, I mean, I think so the point is we don't use remote sensing to estimate potential ET. Potential ET it's physically what, it's a function of the meteorology or what the atmosphere is, from a ability to take in water. The remote sensing approaches that we have here are estimating actual ET. We don't need to know the soil moisture because that soil moisture signal is internal in that land surface temperature signal. Obviously, dry soil heats up faster than wet soil. And also, so you don't need to know the soil moisture stress component. It's really internally in the surface energy balance. There are some, obviously from a modeling standpoint, a modeling method, you do need to know soil moisture because there is, like I said, soil moisture stress is a function of how land surface models estimate evapotranspiration. I think there are some, there have been some work towards developing maybe a more of a hybrid approach where you have and obviously we do this with data assimilation too, of trying to assimilate remote sensing observations in the land surface models. So, I think the main take home is, these methods are estimating actual ET. Knowing accurate soil moisture conditions can help you there, but we don't have that. It's another, we don't have a lot of in situ data for soil moisture. So we must rely on either modeling soil moisture and calculating ET from models, or essentially calculating ET from this thermal signature, which, inherently includes the soil moisture stress component.
Great. Question 11. In another webinar, we were introduced to Landsat's evapotranspiration product, EE-Flux. In the presentation, there was an internet link, but it doesn't work at the moment. Where can I find this 30-meter energy flux product? And we've provided a link below that takes you to a Google Earth Engine app, which uses that product. So hopefully you can click on that and explore some more.
Yeah, and I'll add that, with OpenET, the EE flux method is one of the models that'll be used. So, as OpenET becomes more, we're going through a lot of the beta testing now. So, you know, there'll be a lot more ET data available. At least, the OpenET project is focused on the, the Western US initially, but, I know the EE flux product, you can run that app through and run it anywhere. But and eventually, I think there'll be other methods that will start to, really be able to take advantage of some of the Earth Engine and the cloud computing capabilities.
Great. Question 12. Where can I download ET data?
This is a question where it's probably better for me to come back and edit this later, and I can provide some links to some openly available data. So it just really depends on what your application is too, your focus area, where what resolution do you want data at, what how many what years of data you have. I think a lot of the models that I presented here, some of them are more operational and provide long-term data sets, and also sometimes it's best to contact the PI or the developer of a given tool and ask about. So we can definitely come back to this and provide some links.
Great. And question 13, how is the land surface temperature measured under trees and grasses?
Well, we don't really. I mean, I guess that's, so if you take a two-source energy balance model, we're really looking at the temperature of the bare soil component and then essentially the canopy. I think on some level there is some need in some areas, especially in savannas where you have, more sparse tree cover, but it from a modeling standpoint is difficult, that you need to almost go to a three-source model where you're also trying to model essentially, the under the canopy state. It's kind of one of maybe the weaknesses of the thermal based models, that we're missing sometimes, important processes that happen with heat transfer between under the canopy and the actual atmosphere. So I'm not sure we do that effectively with, from a remote sensing standpoint.
Great. Question 14, what are the differences between plant species when calculating ET using Landsat?
It depends it depends what method you're using. I think some methods, you need to have some characterization of the vegetation. What type of vegetation are you looking at? A nominal height. A lot of methods, use some estimate of leaf area index or the fraction of green leaf in a given pixel. For some of the when we run these on a more regional or continental or global scale, we have to make some assumptions where we don't have a lot of detailed information when it gets down to actual what kind of species. So we tend to keep it more general and generic and categorize the vegetation type. Is it a coniferous forest? Is it a deciduous forest? Is it cropland? Is it shrubland? We don't necessarily discriminate beyond kind of that general land cover classification. Obviously, as I said, especially with the crop coefficient method, you kind of, it is better if you're able to characterize what type of crop it is, just because of the different water use dynamics. So for energy balance, maybe it's not as important, but for crop coefficient it is. And but then again, it gets kind of back to your in situ data where it's like, how much do you have and how much do you need?
Okay, question 15. Multi-sensors are very good at measuring ground temperature. It is very difficult to find the swarm of locusts in the desert. I think the presence of a swarm of locusts can change the surface ground temperature. can we use these multi-sensors to observe the locust swarm activities in the desert?
I mean, this is obviously an important problem right now. And honestly, I'm not sure. I think, we have seen people start to look at trying to characterize, moisture conditions to see where swarms of locusts are likely to be, or where breeding may be more optimal. But I'm not aware of anyone using actual remote sensing to look at changes in temperature due to swarms. But I can ask around, and if I come back with anything, I imagine if you get a dense enough swarm, that might be possible, but you might also be limited by the resolution of what we actually sense thermally right now.
Great. Question 17. Characteristic water use curves use the same days of growing period for all different crops. Is this correct?
Yeah, I think in that study, that's one of the assumptions we're making. Over a growing season, kind of being stable. But I think obviously there are some differences in the length of that growing period, and I think in that case, optimally those were all scaled to where different crops were essentially planted, because we had good information about when those fields were active and when they were not. So yes.
Okay, question 18. In slide 25, which satellite do you use for microwave and how to combine with Alexi?
So there's a number of microwave sensors that provide, so we need that 37 gigahertz observation, a Ka band. There's a number of sensors that have been up over the last 20, 30 years and then are still up. And a lot of those are also processed within the GPM, the Global Precipitation Measurement Mission. They do their intercalibration between, the core GMI sensor and then all these other sensors. So that gives us a number of observations over the diurnal, or the day and night period. And then we use methods to fit those into a diurnal temperature signal. And then there are some corrections because microwave is sensing, thermal's connected, sensing essentially that skin temperature, where microwave, depending on the soil moisture, is looking at a little bit of a different, deeper into the soil. So there is some correction in both the phase and the amplitude of the microwave signal that we have to match back to what we would have seen with thermal land surface temperature. And the other caveat I always like to mention is that the microwave is coarser resolution, but it does give us information in a lot of areas where cloud cover really affects our ability to get retrievals of land surface temperature from thermal. And I can provide the link to where we process our land surface, or I'll provide a link to the raw microwave brightness temperatures that we use in our algorithm.
Okay, question 19. In field level applications for decision-making process, how can EDDI be used as the proxy and how is it tied with ESSI?
I think for, EDDI, as I said, is really driven by that potential ET, or changes in, potential or reference ET. So EDDI will see essentially the atmospheric signal before there's actually any response in the land surface. So EDDI is a really powerful tool to look at potential for development of drought. It can't tell you much about what's actually happening on the ground, but it can tell you the demand that the atmosphere has. And if that's above average, that means it's going to, it can rapidly deplete soil moisture, and then you can start to actually see vegetation related stress. And that's what we see with ESI. We're actually looking at the physical plant response to stress, water stress. So EDDI can't tell you anything about what the plant's actually doing, but it can tell you essentially what the atmosphere, the role the atmosphere is playing in with the land surface. But some of these other methods actually, like ESI, tell you what's actually happening at the plant level. So really they need to be used together, where EDDI is more of a early warning for the potential of drought, and then ESI is actually more of an early warning for actual onset of vegetation stress. or, especially because we can see that stress signature before the plant actually might become damaged or browned. So if you're using only an NDVI, you're going to see it much later than you might see it in ESI. And if you're only using ESI, you maybe didn't see the atmospheric signal that Eddie would have shown you.
Okay, question 20 is very specific to a part of India. So can we get root zone soil moisture data for any region in India at high resolution, or say for a crop, cotton cultivation in the Maharashtra state? And how can we get high resolution crop specific vegetation images, say for time series cotton cultivation in a region of India or through geo coordinates of India?
You know, it is a very specific question. I think from the real answer is no. There's not really a way to directly estimate root zone soil moisture from any satellite. Um, uh, from the high resolution standpoint, there are, with, current synthetic aperture radar and current, future, the L-band SAR from NASA and the Indian Space Agency that's coming online, in the next couple of years, will give us, the ability to estimate, high resolution soil moisture. Also, it's been shown that Cygnus, which is essentially was going to be an ocean wind type mission for, tropical systems, using reflected GPS signals. That is also shown to be a relatively unique way of estimating high resolution soil moisture. So definitely we're moving towards the point where we can get high resolution surface soil moisture, but you still need to rely on modeling to kind of model how changes in surface soil moisture affect root zone soil moisture, because we don't directly observe root zone soil moisture with some of the microwave instruments, either active or passive.
Great. Question 21. There are several types of drought. Does ESI predict hydrological drought?
Generally, no. So, I mean, ESI is really a meteorological or agricultural drought tool. Obviously, hydrological drought happens on much larger time scales, sometimes can be driven with, groundwater dynamics, snow melt in areas where where snow melt relies, a lot of, water use relies on snow melt. So it's definitely not a tool that should be used for predicting hydrological droughts. Sometimes, we obviously, if an area is exhibiting, a long hydrological drought, we'll definitely see that in ESI2 on some sense, that we'll see, obviously sometimes the vegetation is feeling that change in deep root zone soil moisture. So a lot of times there are some events where the two correspond well, but that's there are better tools for doing hydrological drought, and those really are predicated on looking at snow melt, precipitation over these periods, groundwater changes. So yeah, there are times where yes, you can technically use it, but I think we really focus on its capabilities for meteorological and agricultural drought.
Great. Question 22. What is the time delay that we can expect between seeing a signal of plant stress in ESI and NDVI, so the actual
Yeah.
plant damage?
I don't think we know. I mean, I think we kind of estimate, on order of maybe 1 to 3 weeks. It just depends on how rapidly evolving the drought is, but I mean, from a standpoint of really trying to understand, that's kind of still an area of open research. And, I think no specific case would be, it requires us to go back and look at some of these cases where we did see the onset of stress in ESI before you see it in an NDVI or a vegetation index.
Great. Question 23. What are the potential uses of remote sensing based ET monitoring for index crop insurance?
I think on anything, it's like once you get to, so, and it depends, in places in Africa where, field sizes are very small, we really don't, even at, technically, Landsat, the thermal sensor really, is on the order of 100 meters. We can sharpen that down to 30 meters, but when you get to some of these areas with much smaller fields, you know, it's hard to get a pristine view of, water use at a field scale there. But it is areas that we've been working on with, groups that are focused on, index crop insurance. So I think, in the end, as we get to these tools where we're able to, like OpenET, where we're able to actually produce, operational field scale estimates of ET, I think it will have a potential use for being used in some of the, index methods and for crop insurance. So I think you expect to see it probably become a bigger thing as we move forward.
Great. And question 24 is actually similar in terms of small field size. So a majority of farmers in India have 2 small holdings, 2 acres or less on average. How can ET help them plan their crop rotation cycles?
I think, similar to the last question is like, we're really, there is a constraint with resolution. I think as future sensors come, maybe we get to the point where we have higher resolution thermal. But I think also it's just, a lot of these methods are not operationally produced. And as those capabilities continue to grow, it'll make it easier for farmers to start to integrate this into their decision making. Where now it's really getting good, accurate information kind of occurs on the retroactive scale. Something I think going forward you'll see more, but I mean, depending on the size of your fields that you want to resolve, it really is constrained by, our, essentially the technology of, the thermal acquisitions.
Great. Question 25. Why is AVHRR not used in Alexi to achieve a longer time series?
Not because we don't want to. It's just an area of active research for us. AVHRR is complicated in some of the earlier sensors because there's a lot of drift of the sensor where it over time or its life cycle will observe the land surface at a different time as you have orbital drift. So that requires just a more complicated technique than what we've applied for MODIS or VIIRS. But it's definitely an area that we are actively working on. So it's not that we don't plan to do it, it's just a matter of we're not there yet.
Great. And last question, are Alexi and Alexi ESI available at the global level?
Yes. We run both Alexi and the ET and the ESI data from Alexi at about 5 kilometers globally. The ESI is produced near real time and is available for download, and I can add the link here after we're done. And then the ET data is more of a retrospective tool, but we're working on getting it run more of a near real time mode. So yes, I mean, and those kind of serve as the boundary condition for our disaggregation, our disalexi tool, for when we want to run that field scale method over different areas of the globe.
Wonderful. Well, we did it. We got through all the questions. We are at time, so I guess so. Yeah, thank you. And Chris, I want you to know is a lot of the information we've been getting from the participants has been just very positive and very thankful for everything you've been doing. And on behalf of ARSET as well, thank you so much for contributing to this webinar series.
No, happy to do it. Thanks.
Great, and I also want to acknowledge all of the ARSET colleagues that helped make this possible. That's Dr. Amita Mehta, Dr. Erica Podest, Selwyn Hudson-Odoi, Brock Blevins, and Jonathan O'Brien. So thank you all. Thanks everybody for joining. And again, the homework is due on May 12th, so please get that in. And all the content from the Q&A session, as well as the materials from the presentation are up on the website. So please go there to access them. And hope you all stay safe, and we'll see you soon. Thank you.